Let us start today's class. Measurement of resistance and sensitivity of bridges will be discussed in today's class. You know, Wheatstone bridge is used for the measurement of medium resistance. So today I'm discussing about measurement of resistance using Wheatstone bridge. You are saying you're looking at the diagram. The bridge consists of 4 resistive arms together with a source of EMF and a null detector. The galvanometer is used as a null detector. This complete figure shows the basic Wheatstone bridge circuit. The arms consisting the resistances PQRS. They are PQ are called ratio ohms, and this is called standard resistance, standard ohm, and this resistance is called, that is R is called the unknown resistance, that is this one. This is to be measured. The battery is connected between A, you can see the battery that is connected between A and B, while galvanometer is connected between B and C. So when the bridge is balanced, the galvanometer carries zero current and it does not show any deflection. Thus, bridge works on the principle of null deflection or null indication. To have zero current through galvanometer, are you getting? Students, please look at the diagram. This, when zero current through the galvanometer, the points, this D and C, you can look at that, the points D and C must be at the same potential. Thus, potential across AD must be same as the potential across AC. Thus, I1 into P should be equal to I2 into R, or I1, I3 into Q should be equal to I4 into S. As galvanometer current is zero, I1 will be equal to I3 and I2 will be equal to I4. Considering the battery path under balanced condition, I1 is equal to, let me have the, you can see there, I1 is equal to I3, which is equal to E divided by P plus Q. Like that, I2 is equal to I4, which is equal to E divided by R plus S. Thus, using this equation, both the equations, you can derive the relation and you will land up with the final relation. See here, R by S is equal to P by Q, which is equal to R. R is the unknown resistance, which is equal to PS by Q. This is actually required balanced condition of Wheatstone bridge. The following points can be observed. What are those? It depends on the ratio of PQ, and hence these arms are called ratio arms. As it works on null deflection or null indication, the results are not dependent on the calibration and characteristics of galvanometer. The standard resistance, yes, can be varied to obtain the required balance. These are the important things. So next, the topic, what I'm discussing is sensitivity of Wheatstone bridge. What do you mean by sensitivity? When the bridge is balanced, the current through galvanometer is zero. But when bridge is not balanced, current flows through the galvanometer, causing the deflection. The amount of deflection depends on the sensitivity of the galvanometer. This sensitivity can be expressed as amount of deflection per unit current. You can look at this. Sensitivity S is equal to deflection D divided by current I. Now, as the current is in microampere and deflection can be measured in mm, radians or degrees. So the sensitivity is expressed as millimeter by microamps or degrees per microamps. You need to have, it's very, very important to understand. Please look at that, the measurement, because we are talking about the measurement subject. So more is the sensitivity of a galvanometer, more is its deflection for the same amount of current. So another way of representing the galvanometer sensitivity is the amount of deflection per unit charge. You can look at this relation. What did I say? The amount of deflection per unit charge, per unit voltage across the galvanometer. This is called voltage sensitivity of the galvanometer. Mathematically, it is denoted like this: SV is equal to theta by E, where this E is equal to voltage across the galvanometer and theta is equal to deflection of galvanometer. While the bridge sensitivity is defined as the deflection of the galvanometer per unit fractional change in the unknown resistance. It is denoted as SP is equal to bridge sensitivity is equal to theta divided by delta R by R, where this delta R by R is equal to unit fractional change in the unknown resistance. Hope you understood. So next is how it is derived. How do you derive the sensitivity of the bridge? You can see that when the bridge sensitivity can be calculated by solving the bridge for small unbalance. So at balance condition, what happens? This condition will be fulfilled. So when I derive that, when the resistance is changed by delta R, creating the unbalance, due to this, the EMF appears across the galvanometer. To obtain this EMF, we have to use Thevenin's method, but that is we have to remove the branch of the galvanometer and obtain the voltage across the open circuit terminals. That is how it is done here. Okay, the calculations, what we are doing here is, this is how the galvanometer, how it is calculated. So finally, from the galvanometer, see how we are creating the unbalance and we are calculating the sensitivity of the Wheatstone bridge. So bridge sensitivity, what I told is given by, first we have to calculate VThevenin. When we calculated VThevenin, that should be substituted here. That we have to find the bridge sensitivity, which is given by SP is equal to theta by delta R by R. Then that delta R by R is equal to delta R by that, whatever the small change you have done. That is, that as there is change in the resistance, what R resistance, unknown resistance, PQSR, that is. Okay, so from the galvanometer sensitivity, we have to calculate theta, and using theta in the expression of SB, we will finally land up with the relation SB is equal to bridge sensitivity is equal to E into SB, this relation, students. Okay, so this is, thus the bridge sensitivity depends on the bridge parameters, the supply voltage, and the voltage sensitivity of the galvanometer. So for higher or lower values of what you said, that resistance is S by R, will be, the sensitivity decreases considerably. For higher or lower values of S by R, the sensitivity decreases considerably. So this is about the sensitivity of Wheatstone bridge. So we have some advantages of Wheatstone bridge. See, what are the advantages? See, the results are not dependent on the calibration and characteristics of the galvanometer because it works on null deflection. Second advantage is the source EMF and inaccuracies due to the source fluctuation will not affect the balance of the bridge. Hence, the corresponding errors are completely avoided. So final advantage is due to null deflection method used, the accuracy and sensitivity will be higher than direct deflection meters. So these are the few advantages of Wheatstone bridge. So that is actually the ending of this class. So today what all I have discussed is about Wheatstone bridge, sensitivity of Wheatstone bridge, and the advantages of Wheatstone bridge.